Okay guys, I'm going to be talking through the solution to a couple more of the homework problems. We're going to be looking at problems 30 and 31 here. Problem 30 gives you a problem description of an auto company trying to figure out a production plan to maximize its profit by producing cars and trucks. It gives you some information in these bullet points that helps you understand the constraints. Then it says a truck is worth $300 in profit, a car is $200 in profit, and to assume fractional cars and trucks. Then it spits out an LP for you in part A, and it asks you to explain why this LP determines a daily production schedule that maximizes company profits. And the explanation it tells you to give it is define the decision variables and describe each constraint. Okay, I've already done that here, but I'll just sort of walk you through it. Essentially, you figure out X1 and X2 pretty quickly are cars and trucks, or trucks and cars. And if you look and see that each truck contributes $300 to profit, well, that's the 300 you see right there, which means that X1 is the number of trucks to produce per day. That makes X2 the number of cars to produce per day. Okay, so we define the decision variables. Now all that's left to do is describe each constraint. Okay. So essentially, if you read and understood the problem, it's not too bad to figure out. But what you see, this first constraint says that 1/40th of the number of trucks produced plus 1/60th of the number of cars produced per day is less than or equal to 1. And if you see up in the problem, it talks about the paint shop being able to produce as many as 40 trucks per day, as many as 60 cars per day. So essentially this first constraint is what I call the paint shop capacity constraint. And that constraint just ensures that the daily production plan doesn't exceed the capabilities of the paint shop. And the second constraint is just analogous for the body shop. You see it says 1/50th times the number of trucks plus 1/50th times the number of cars less than or equal to 1. And the body shop, interestingly, can produce 50 cars or 50 trucks. So this constraint just ensures that the daily production plan doesn't exceed the capabilities or the capacity of the body shop. So I call it the body shop capacity constraint. Okay. Part B then says to write the dual of the LP, and you've done that a lot, so it's probably becoming hopefully easier for you. I'm going to skip ahead and show you the dual and talk about part C, which is the economic interpretation of the dual problem. So that's what you see here. I've boxed in the dual. It's min y1 plus y2. Then we have two constraints that enforce some relationship about y1 and y2, and y1 and y2 are positive. Okay. So giving the economic interpretation of the dual to me means first interpret what are the decision variables. Okay, and I've done that here. I said y1 and y2 are the price paid for the paint and the body shops. Okay, simple as that. Then constraint, the second part I should say of interpreting the dual is to tell me what do these constraints enforce. Okay, and you see I've done that here in 2. What I've said is that constraints ensure that the resources required to build a truck or a car cannot be valued less than the truck or car that they could equivalently produce. So what I mean by that is this. It takes 1/40th, you could think of it this way, 1/40th of a paint shop and 1/50th of a body shop to produce a truck. So in other words, the prices that the auto company would be willing to accept for its paint and its body shops should be at least what they get by if they use those resources to produce a truck or a car. In other words, just what I said. The resources required to produce a truck or a car in total can't be valued less than that truck or that car that they could equivalently produce. And so this first constraint is related to the resources that could be used to produce a truck, and the second one, the resources that could be used to produce a car. And the last little bit is I said, okay, the objective function is going to be to minimize the total price paid for the auto company's resources. So I did pretty bad English grammar here. The auto company possessive resources. Sorry about that. Okay, I'm going to go back and move on for the sake of time and look at problem 31, which you see here. Okay, so it gives us, again, an LP. The first thing it says to do is write the dual. We're getting familiar with that, so I've done it for us. The primal had 4 decision variables. The dual has 4 constraints. You see them there. Part B asks you, to graphically determine an optimal solution for the dual. And if you do that, what you'll end up with is something like this. The 4 constraints all are sort of diagonal in this region close to the origin. They're all greater than or equal to constraints, so they all point in the same direction, which is nice. And when you solve it, you find that there's an extreme point right here that turns out to be the optimal solution. Again, you would do that by graphing the isoobjective line, moving it in a minimizing direction, finding the last point in the feasible region that you can get to. Anyways, the point is that this extreme point, which is optimal, is determined by the intersection of constraints C1 and C4. Or we would say that C1 and C4 are binding constraints, okay? Turns out the other 2 constraints are slack, okay? That's just what I've said here. C2 and C3 are slack. Let me try and move this up a little bit. There we go. Okay, we're going to use that information in part C, which asks us to use complementary slackness to determine which 2 decision variables of the primal problem are equal to 0 in an optimal solution. Okay, so again, we can use information about the optimal solution of the dual to tell us something about the optimal solution of the primal. Particularly, recall what complementary slackness says. Complementary slackness says that the product of, for any constraint, the slack in that constraint and the dual variable of that constraint, or the shadow price of that constraint, have to be 0. Okay? So that tells me something particularly for constraints 2 and 3. Since constraints 2 and 3 have positive slack, that means this, that the dual variables associated with constraints 2 and constraint 3 are equal to 0. Okay? So in other words, let me label these constraints C1, C2, C3, C4. The dual variables associated with the second and third constraint at the optimal solution are going to be 0. Okay? Now this is the part where you sort of have to understand duality. This is the dual of my original LP. Okay? The dual of the dual will be the primal LP. That means that the dual variables associated with these constraints are actually going to be x1, x2, x3, and x4. In other words, my original primal decision variables. Okay? This complementary slackness result told me that the dual variables, that's what I meant by DV here, the dual variables associated with constraints 2 and constraints 3 are equal to 0 in the optimal solution. That tells me that x2 and x3 are equal to 0 in the optimal solution. So that's what part C is trying to drive at. That since constraints 2 and 3 are slack in the dual, that tells me that the dual variables associated with those constraints in the dual, which happen to be my original primal decision variables x2 and x3, are in fact 0. And I can use that to help me solve the original problem. So part D asks to graphically determine the optimal solution for the LP that uses that complementary slackness information. Essentially what you can do is say x2 and x3 are 0. I'm going to come back to my primal and just pretend they're not there. I know they're going to be 0 at the optimal solution, so now I've got a much simpler LP to solve, and in fact now it's just got 2 variables, x1 and x4. You could do the graphical solution and solve that, and that's what part D asks you to do.